$2.3 billion. A steel arch wider than a football field, built to isolate the remains of Chernobyl Reactor 4 for at least 100 years. On February 14, 2025, an explosive drone punches through the roof. Fire spreads inside the layered skin. 8 years after the arch slides into position, one impact damages the barrier designed for a century. The load-bearing frame stays standing. Radiation monitors show no immediate release. The structure does not collapse, but the damage reaches the systems that make the arch more than a roof. The inner and outer cladding are breached. Ventilation is compromised. The sealed environment begins to behave like an open building. By December 2025, an international inspection concludes that the new safe confinement has lost its primary safety functions, including confinement. The arch still dominates the site. 110 meters high, 257 meters across, 162 meters long, 36,000 tons when fully equipped. Beneath it sits the first shelter, a concrete and steel structure erected in 1986 in 206 days. Beneath that sits the destroyed reactor. Roughly 185 tons of nuclear material remain inside in fragments, dust, solidified lava-like masses, and secondary uranium compounds. The new safe confinement was built to separate all of that from the weather. It was also built to create a controlled workshop around the old shelter, a place where machines could dismantle unstable beams without sending contaminated dust into the atmosphere. A century of controlled access. A century to remove structures, package waste, and decide what to do with material that no worker can safely approach by hand. The first shelter never had that capability. In April 1986, Reactor 4 is torn open during a failed systems test. The explosion destroys the upper part of the building. Graphite burns. Fuel and structural material melt together. Concrete, sand, lead, steel, and nuclear fuel form new masses inside rooms that become inaccessible within minutes. Construction begins while the reactor is still hot. Crews pour concrete from protected positions. Helicopters carry materials over the open core. Crews install beams using remote methods because radiation fields make normal assembly impossible. Welding cannot be completed at many joints. Large elements rest on damaged walls whose exact condition is unknown. The shelter closes around the reactor after 206 days. Fast enough to reduce releases, not precise enough to become permanent. The roof and walls later contain cracks with a combined area measured at about 1,000 square meters. Rain and snow enter. Water moves through radioactive material. Steel corrodes. Concrete shifts. Dust accumulates in rooms that cannot be fully surveyed. By the 1990s, engineers know the first shelter is running on borrowed time. Only part of the interior can be inspected. Some areas remain blocked by debris. Others carry dose rates that stop direct human access. Stabilization work strengthens vulnerable walls and roof elements, but the work only extends the structure's useful life. It does not remove the fuel. It does not dismantle the unstable frame. It does not seal the building for a century. In 1995, Ukraine, the G7, and the European Commission begin defining a larger solution. In 1997, the Shelter Implementation Plan sets out the work. Stabilize the old shelter. Build a new confinement. Create systems for dismantling and radioactive waste management. More than 40 donor countries and institutions eventually support the program. The full plan is estimated at about 2.15 billion euros, roughly $2.3 billion. The arch itself costs about 1.5 billion euros. The plan does not move directly from paper to steel. The old shelter has to survive long enough for the new one to arrive. From 2004 to 2008, crews reinforced the western wall, emergency slabs, roof zones, and supports beneath massive existing beams. Preparatory work for the new confinement begins in 2005. By 2010, the erection site is ready. Full arch assembly starts in 2012. 15 years pass between approval of the shelter implementation plan and the first major steel rising beside Reactor 4. That delay reflects the site. Survey crews cannot walk freely through the building they are measuring. Drawings from before the accident no longer match the wreckage. Radiation maps control where people stand and how long they stay. Foundations must carry a 36,000-ton moving structure without transferring load into the unstable sarcophagus. End walls must close around existing buildings while remaining structurally independent from them. The project is designed around something engineers cannot touch, cannot fully see, and cannot allow to fall. The idea looks simple from a distance. Build a giant steel shell. Place it over Reactor 4. Keep water out. Keep contaminated dust in. The engineering underneath is more complicated. The arch is not one layer of metal. It is a controlled environmental system. Two skins cover a tubular steel frame. The outer cladding blocks rain, snow, and wind. The inner cladding separates the steel from the contaminated interior. Between them sits an annular space. Ventilation equipment pumps dry, warm air through that space. Relative humidity must stay low enough to slow corrosion across tens of thousands of tons of steel. Pressure matters too. The air system helps maintain a controlled pressure difference across the layers. If dust rises inside the old shelter, airflow should not carry it directly outside. The arch contains the release. Filters and monitoring systems track what moves through the air. A breach in the cladding does not have to bend the main frame to damage the confinement function. It only has to break the controlled envelope. Humidity is the quiet design limit. Warm air can hold more moisture than cold air. If humid air reaches cold steel, water condenses on the surface. Paint and coatings slow the reaction. They do not stop it for 100 years. The ventilation system keeps the annular space warm and dry, so the steel stays above the dew point. Sensors measure the condition continuously. Fans and heaters correct it before droplets form. That is why the cladding is structural to the mission, even when it carries little of the arch's main load. The tubular frame holds the shape. The skins hold the environment. Damage either one, and the facility loses a different function. The arch shape solves several problems at once. It leaves a clear span over the old shelter. No new columns descend into the destroyed reactor building. Loads travel down both sides into foundations outside the most dangerous interior zone. The curved roof carries snow and wind, while leaving enough height for cranes to move above the sarcophagus. The two end walls perform a different task. They close the volume around buildings that were never designed to receive a second enclosure. The new walls approach the old plant, but do not depend on the damaged shelter for support. Flexible seals close irregular gaps. The arch can move with temperature. The old concrete can continue settling. The controlled envelope must remain closed around both. The completed complex contains 19 major substructures. Foundations, east and west end walls, fire systems, water treatment, backup power, radiation monitoring, seismic monitoring, structural monitoring, industrial television, decontamination areas, waste fragmentation and packaging spaces, a ventilation network large enough to manage the atmosphere around a building the size of an aircraft hangar. 2 bridge cranes hang beneath the roof. Their combined system is designed for loads up to 1,500 tons. Operators work from protected control areas. Cameras look down onto the old sarcophagus. Tools attached to movable platforms. The cranes are supposed to cut, lift, stabilize, and remove structures that no crew can safely dismantle from below. Workers prepare the site west of Reactor 4. The distance is only a few hundred meters, but it changes the entire construction method. The arch cannot be assembled directly above the reactor. Radiation exposure would make years of work impossible. So the structure is built in a cleaner area, then moved as one piece. Workers strip contaminated soil and cover parts of the erection zone with concrete. Foundations rise on both sides. Steel components arrive from factories across Europe. Each member is marked, checked, and moved into position. The arch is too large to assemble at full height in one lift. Crews build it in sections. Two enormous halves take shape beside the reactor. Workers align tubular members and install bolts. Around 650,000 bolts hold the structure together. A single bolt costs about €25. Under-tightened, the connection moves. Over-tightened, the thread fails. Every joint must land inside a narrow range. The total bolt value alone approaches €16 million. Workers lift the first sections to an intermediate height. New steel is added below. The process repeats. Build low, lift, build again. The two halves rise until their crowns reach about 110 meters. In 2015, crews join them into one arch. Workers install the double cladding across the curved surface. Exterior panels must survive temperatures from about -43°C to +45. The design also accounts for extreme wind, a Class 3 tornado, snow loads, and an earthquake. Every penetration through the skin needs a seal. Every seal becomes part of the 100-year promise. Workers mount ventilation ducts, sensors, cameras, power systems, fire equipment, and the bridge cranes. The steel shell becomes a machine. Thousands of components must operate together before the arch can move. A roof without ventilation will corrode. A crane without cameras cannot dismantle the shelter. A sealed volume without monitoring cannot be trusted. By November 2016, the structure weighs 36,000 tons. It stands 327 meters from its final position. The path ahead crosses contaminated ground toward Reactor 4. Rails and skidding tracks carry the load. 224 hydraulic jacks push against the base. Workers start the slide. Each stroke moves the arch about 60 centimeters. Pressure rises. The structure advances. The jacks reset. Another 60 centimeters. The full movement requires about 40 hours of active skidding spread across several days. The arch travels slowly enough to watch from the ground. A building taller than the Statue of Liberty moves across the site without wheels. Alignment stays within tight tolerances. The east and west ends approach the prepared walls. On November 29, 2016, the new safe confinement reaches its design position above Reactor 4. The move succeeds. No major structural failure, no uncontrolled release. The largest movable land-based structure ever built now covers the old shelter. Compared with the 206-day sarcophagus, this is a different kind of engineering. Measured, instrumented, bolted, ventilated, designed around work that will continue for generations. The project is not finished in 2016. Systems testing continues. Workers connect the end walls, commission the ventilation, test the cranes, verify monitoring networks, and run emergency procedures. A 72-hour trial operation is completed in 2019. The structure is handed over to Ukraine that July. In 2021, the integrated confinement complex receives its operating license. The arch buys time. It does not remove the reactor. Roughly 95% of the original fuel remains inside the shelter object. Some material sits as recognizable fragments. Some has mixed with concrete and steel. Some has broken down into fine radioactive dust. The old structure still contains beams and slabs whose condition is difficult to confirm. A successful cleanup elsewhere shows the difference. After the 1979 accident at 3 Mile Island, Unit 2 in the United States, crews remove about 99% of the damaged fuel inventory. Defueling finishes in 1990, roughly 11 years after the accident. Chernobyl reaches 2025, with most of its original fuel still inside. The reactor is more heavily destroyed. The material is spread through more rooms. The surrounding building is less stable. The arch exists because normal defueling methods do not exist here. Inside the new safe confinement, the sequence is supposed to be controlled. Inspect, stabilize, cut, lift, lower, fragment, package, store. Repeat for years. The cranes create distance. The cladding creates containment. The ventilation creates a dry, managed environment. Remove one of those systems and the work stops. February 14, 2025, early morning. A high-explosive drone reaches the Chernobyl site. Ukrainian authorities identify it as Russian. Russia denies responsibility. The International Atomic Energy Agency does not assign attribution. The impact hits the roof of the new safe confinement. The outer cladding opens first. The energy continues through insulation and reaches the inner layer. A breach of about 15 square meters cuts through the envelope. Around 200 square meters of panels are damaged. The strike also affects systems connected to safe work inside, including crane and ventilation equipment. Fire spreads through material inside the roof assembly. From the ground, the steel frame still looks intact. The more difficult fire sits between layers. Emergency crews cannot simply drive a hose to the point of impact. The damaged area is more than 100 meters above the ground. Access is limited. Smoke and heat move through enclosed spaces inside the arch skin. Workers and emergency responders open sections of cladding to reach smoldering insulation. Water enters a structure designed to keep water out. On February 17th, 93 emergency personnel and 17 units of equipment are working at the site. Hotspots remain. The fire and smoldering take several weeks to extinguish completely. Radiation readings remain within normal limits. No immediate radioactive release is detected. The main steel arches do not fail. The old shelter does not collapse. The first result is visible as a hole in the roof. The larger result is hidden in airflow, moisture, pressure, and equipment status. The original design depends on separation. Outside weather, dry annular space, contaminated interior. 3 different environments divided by cladding and controlled by ventilation. The strike connects spaces that were meant to remain separate. Rain can enter through damaged panels. Humid outside air reaches steel kept dry since commissioning. The pressure difference becomes harder to maintain. Ventilation that once moved air through controlled paths now faces openings it was never designed to manage. Corrosion begins as a schedule, not a dramatic event. Moisture settles on steel. Protective systems work outside their intended range. Years disappear from the design life. Temporary repairs start quickly. Workers cover openings and seal sections of the inner and outer cladding to reduce water ingress. Engineers inspect the load-bearing frame. Monitoring systems continue to operate. The immediate objective is not to restore the full 100-year design. It is to stop the damage from multiplying. In April 2025, the IAEA reports that the structure can still perform a protective role, even after extensive damage. The assessment continues. More areas become accessible. More systems are checked. By late November, an international team completes a wider safety review. The conclusion changes the status of the arch. The main load-bearing structure has no permanent damage. Monitoring systems remain available. But the new safe confinement has lost its primary safety functions, including confinement capability. Limited patches exist. Full environmental control does not. The difference is technical. Standing is not the same as confining. A bridge succeeds if it carries load. A roof succeeds if it keeps out weather. The new safe confinement must do both while maintaining controlled pressure, low humidity, filtered airflow, remote handling, radiation monitoring, and a sealed work volume. The frame can remain straight while the facility fails its main operating requirement. Repairing it means rebuilding systems across a contaminated nuclear site during an active war. The damaged panels sit high on a curved roof. Some work must occur near openings connected to the radioactive interior. New sections have to match the original double cladding geometry. Seals must survive decades of temperature movement. Ventilation must be balanced again. Crane equipment must be inspected and returned to service. Pressure and humidity tests must prove that the envelope works as one system. Workers cannot treat the opening like a warehouse roof. Every removed panel changes containment. Every temporary access route changes airflow. Tools, fragments, insulation, and water require radiological control. Crews need fall protection at more than 100 meters. Work stops during security alerts. Equipment crosses checkpoints into a controlled zone. The repair method must limit exposure before permanent construction begins. The cost follows the complexity. The original arch costs about 1.5 billion euros. Preliminary estimates place full restoration at no less than 500 million euros, roughly one-third of the original construction cost to repair damage from one impact and the fire that follows. The target date is 2030. That date is tied to corrosion risk. Leave the envelope open too long, and the steel frame begins losing the controlled environment that supported its 100-year life. Repair the panels without restoring ventilation, and the problem remains. Restore ventilation without sealing the envelope, and dry air escapes. The entire system has to return together. In April 2026, donors approved 30 million euros for early engineering and procurement work. The repair program is divided into 3 phases. First, collect technical data, inspect targeted areas, and develop repair concepts. Second, turn those concepts into engineered solutions with the Ukrainian regulator. Third, prepare detailed designs, procurement documents, and long lead orders. The phased plan avoids building the wrong repair. The original arch took years of surveys, mock-ups, lifting studies, and systems integration. The damaged arch now requires the same discipline under worse conditions. Engineers need to know what heat did behind the panels. They need to map deformed supports, wet insulation, failed seals, damaged ducts, electrical systems, and crane components. The whole is visible. The repair boundary is not. Workers continue temporary protection. Inspectors track humidity. Sensors watch the old shelter. The arch remains above Reactor 4, still carrying snow, wind, and its own 36,000-ton mass. Beneath it, the fuel-containing material remains where it was. The dismantling mission waits. The timing defines the project. The first shelter takes 206 days to build and remains for decades. The new safe confinement takes years of international planning, 1.5 billion euros for the arch, and 650,000 bolts. It is designed for at least 100 years. The slide finishes in November 2016. Final handover comes in July 2019. The strike comes in February 2025. 8 years after the move. Less than 6 years after handover. One breach of 15 square meters, around 200 square meters of damaged panels, several weeks of fire. At least 500 million euros in projected repairs. Full restoration targeted by 2030. The steel frame still stands. The cranes wait above the old sarcophagus. Roughly 185 tons of nuclear material remain below. The $2.3 billion program created a century-long barrier. Now that barrier needs a second international construction project before its first decade is complete. Subscribe for more engineering stories.